Okay, this is my video number 12. We're still dealing with the system of x dot equal to ax plus by and y dot equal to cx plus dy. Right. So in the previous video we dealt with first case where where we have a real and distinct eigenvalue. Right. So now for this case we consider this is we call it as case 2, right? Case 2, we consider the lambda 1 and lambda 2 are complex conjugate, complex conjugate, where in this case we have so remember that our roots is given by, I think, a minus just a minute, we have a minus so we have half a plus d plus minus square root a minus d squared plus 4bc. That okay. So to have the complex conjugate, of course we need everything inside the square root must be negative. Okay, so that's the case we consider. So for this case, for the lambda 1 lambda 2 complex conjugate, so the condition we need is that a minus d squared plus 4bc is negative. Okay, so if we complex, we may consider now, or we may assume that lambda 1 as of the form u plus iv and lambda 2 is u minus iv, where uv are real constant, uv are real constant. So then we do the transformation. The purpose is still similar as I discussed earlier in the previous video. So we do the transformation. Zeta equal to cx plus u minus ay, this is a, and eta as a v vy. So this transformation, we transform our system, this system. I think if I'm not mistaken, I denote this as a equation 1. You can check those things. So but doesn't matter. In this video I denote this as a equation 1, as easy for me to refer. We transform equation 1 into we have zeta dot equal to u zeta minus v eta and eta dot equal to v zeta plus u eta. Okay, so therefore we may consider the system x dot equal to ux minus vy and y dot equal to vx plus uy. So where u and v are real. So again, this transformation actually, it will not distort the trajectories of the system. It just either rotate the trajectories or magnifies or shrinking the trajectory. So we can still consider this transformation will make our life much easier. So now consider that we have, okay, this is the root that we have, okay, from that system. So we still consider those system. This explanation here just to show that system x dot y dot equal to all these things with such a roots complex conjugate, where we have the condition for that is everything inside the square root is negative. Okay, we may after doing that transformation, so we can write the original system that into that system and this system. Okay, now comes to the condition to determine the properties of the knots, the properties of the or the behavior of the trajectories. Okay, so we have two cases here. First case is that lambda 1, lambda 2 are purely imaginary. Yeah, imaginary. For this case, we have a plus d equal to 0. Okay, so if you consider the original system, a plus d, which is that part, if this is 0, of course, what happened there, we only have the absolute purely imaginary. Okay, we only have purely imaginary case. So that's we consider for purely imaginary, a plus d is 0. Okay, so then what happened to our roots is that we have lambda 1 is just iv and lambda 2 is negative iv, because lambda 2 is conjugate of the of lambda 1, where u is 0, where this uv is from that. Yeah, this is our we assume that lambda 1 lambda 2 is, because this is a general form. Okay, now having that condition, so what happened to the system? You're going to have the system become x dot equal to minus vy, y dot equal to vx. Okay, and with that system, we have the solution for this. We have the solution for that system is that x is c1 cos vt plus alpha, and yt is c2 sin vt plus alpha. Okay, so this is the general solution to that system. And for this, you can see if you square both sides, what we're going to have is that x squared plus y squared equal to c1. This is c1, sorry. We have c1 squared, which is the family of circle. Yeah, so the trajectories are a family of circle. Okay, family of circle, where we have, if I did not see as a trajectory, so we have x squared plus y squared is equal to c1 squared. So we can see for a circle, okay, let's say this is our trajectory, 0, 0 is there, our critical point. So this is our trajectory. It's a circle. So either that direction or that direction, if you take t goes to infinity, so what happened, it just goes around that circle, around and around. So we're not approaching the critical point 0, 0. Okay, so in that case 0, 0 is a stable knot. Yeah, so therefore 0, 0, also known as center is stable knot, a stable knot, but not asymptotically stable. Okay, now for the direction of trajectories, So this is what we have. Then I go to the direction of the trajectory. This trajectories is for the transform system. Yeah, for the transform system. Then for the original system, which is equation 1 here, that system, original system, this is the transform system. This transform system, we obtain that trajectories. For the original trajectories, we may have something like could be ellipse. Yeah, direction again I will discuss in a minute. It could be ellipse, either that direction or that direction, we don't know, or could be just as well as circle. Okay, but still the property is the same, which is stable but not asymptotically stable, because as t goes to infinity, just the point just moving around that ellipse. Yeah, so it will not come close to a critical point. So that's why we call it as a stable but not asymptotically stable. Now for the arrow, okay, for the arrow, so we have, this is our trajectory. Let's consider the transform system first. Now we want to determine the direction of that trajectory. So the direction of trajectory depend on C. Yeah, depend on C. Yeah. So if C is negative, then it goes clockwise. If C is positive, then it goes counterclockwise. Yeah. So you can see this by looking at the say y dot say d, if d is 0. Yeah, if d is 0, then we can, let's say we have c y dot is equal to ci. We have that system, then you can find the direction of those. Okay, so for this case, so if c is positive, yeah, if c is negative, so we have clockwise, so which means the direction is that. Okay, and this is for c negative, and for c positive, so we have a circle, and the direction is that side. Okay, this is for the transform system. For the original system, if it's transformed into the ellipse, then the direction is still the same. Okay, now I go to the second case, where lambda 1, lambda 2 are complex. Yeah, complex. In this case, we have a plus d is different than 0. So if you look at the roots, yeah, roots that I've written earlier, lambda 1, lambda 2 is given by that for this system. Okay, so in order to have a complex, not purely imaginary but complex, so means we have the real part, we have the imaginary part. So a plus d cannot be 0. So if this is not 0, then we have the complex, because this part, if fixed already, this is negative, so which means we have a complex roots. Yeah, for the complex roots where a plus d is different than 0, so the solution of the transform one, I think I better give you for this. This is the previous page. Okay, so let's call this equation 2. Okay, that's 1, that's 2. All right. No, not this one. The transform one, that one. Okay, sorry about this. Okay. All right. Now, for lambda 1, lambda 2 are complex. Remember that we have a real parts, we have imaginary parts. So the solution of that, then the solution of 2, the solution of 2, given as xt is equal to c1 e ut cos vt plus alpha, and y t is equal to c1 e ut sin vt plus alpha. So the trajectories, for that, to determine the trajectories, of course you need to look at the x and y, and you have to investigate what happened if t goes to infinity, what happened to x, t goes to infinity, what happened to y, and so on and so forth. But in this case, you can see we have a sine and cos, which means you can always do x squared plus x squared and then y squared and then plus together. Then what we have, this cos squared sine squared give you 1. So what left is only x squared plus y squared equal to c1 squared e to ut. Okay, so in this case we can see that it's just that part give you a circle, but this will either shrink or away from the critical point. Either it goes to the critical point or away from the critical point, depend on u. If u negative, it goes to the critical point. If u is positive, then it goes away from the critical point. So it looks like a spiral, right? So in this case we have, this case is that, so therefore 0, 0 is a spiral point or spiral knot, or we go also known as focus. Yeah, and it is stable, and it is asymptotically stable if we have a plus d over 2 equal to u and negative. Yeah, and as I mentioned to you just now, that when u is negative, as t goes to infinity, that part goes to 0. So we have that part also 0, that part is also 0. So we have x and y approaches the critical points. So in this case we have, if you want to plot the trajectories, so we have the trajectories approaching the critical point, so that it points inside. Yeah. Okay, so if the other way, if a plus d, u is positive, if u is positive, yeah, if a plus d over 2, which is u, is positive, so what happened here, u is positive when t goes to infinity. Yeah, when t goes to infinity, we have that part goes to infinity, so x plus y, x squared plus y squared also getting bigger and bigger, means goes to infinity. And if you look at x and y, that part goes to infinity, this part goes to infinity, so which means xy goes far from the critical point. So we have the our trajectories look like that, and it goes away from the critical points. Okay, and I think I have time for a short example, so I'll give you a couple of examples, but I won't explain in detail this example because the explanation is just similar to the one that I present earlier in the previous video. I think preview number 10, if I'm not mistaken. All right, so the example we have, I give 3 example: minus x plus 3y, y dot is minus 2x plus y, b we have x dot x minus 2y, y dot 3x minus 3y, and c x dot 2x plus 2y, y dot minus x plus 3y. Okay, so in this case, for those 3 example, we have a minus d squared plus 4bc that give you negative. You can check for example number 1, you have minus 1 plus this plus 0, sorry, minus 1, sorry, minus 1, so we have minus plus 2, right? Minus 2 squared plus 4 plus 4 b 3, so 12, so minus, you got negative for this case, as well as that, and as well as example C. So for A we have a plus d, this is 0, so we have, for a plus d is 0, so we have a stable zero point. Okay, you can check detail for I mean find the AB and find the a plus d and find the delta eigenvalue and then so on. Okay, and then for B we have a plus d is negative, so you can check B, a plus d, you got 1 minus 3 minus 2, so you got negative. Okay, and sorry, this one is spiral, yeah, center, sorry, this one is center. And for B, this one is a stable spiral point, so which means for the case B we have it goes inside, yeah, it goes inside toward the critical points. And for the case C, we have a plus d is positive, so it is unstable spiral points. So because we have that goes inside, that goes outside. Yeah. For A, you have family of circle. Direction depend on C. If C is negative, so it goes to, I think, counterclockwise. Where is it? Where's my notes? If C is negative, so it's clockwise, so it goes that way. Alright, so with that example, so I complete the second case. In the next video, I'll talk on the case 3 where we have a double roots. Yeah, double roots means repeating roots. All right. So for now, I stop here. Thank you.